Picture this: one moment, you're scrolling through your phone, checking the latest updates, and the next everything goes dark. Not just your screen, but the entire world. Streetlights flicker out, planes lose communication, and even the hum of your refrigerator falls silent. This isn't the plot of a sci-fi movie. This could be the reality of a massive solar flare striking Earth. These explosive bursts of energy from the sun have the power to disrupt the very fabric of modern life, leaving us vulnerable in ways we rarely consider. In this video, we'll dive into the science behind solar flares, uncover how they could cripple our technology, and explore what it means for humanity's future. From the sun's fiery surface to the delicate systems we rely on every day, this is a story of cosmic power and human fragility. So, where are you joining us from, and what time is it there? Let's begin this journey together. Now, let's take a closer look at what solar flares actually are. Imagine the sun as a colossal, seething ball of energy, its surface constantly churning with activity. Solar flares are sudden, intense bursts of radiation that erupt from the sun's surface, often near sunspots, those darker, cooler regions where magnetic fields are incredibly strong. These flares are born from a process called magnetic reconnection, where tangled magnetic fields snap and realign, releasing enormous amounts of energy in the form of light, heat, and charged particles. Think of it like a rubber band stretched too far. When it finally breaks, the energy stored within is unleashed in an instant. Solar flares are classified based on their intensity, with the most powerful ones labeled as X-class flares. These are the giants, capable of releasing energy equivalent to billions of atomic bombs. M-class flares are moderate, while C-class flares are smaller, but still significant. Even the smallest flares can have an impact, but it's the X-class events that truly capture our attention, as they have the potential to disrupt life on Earth in profound ways. The sun's surface is a dynamic, ever-changing landscape, with magnetic fields constantly shifting and interacting. When these fields become too twisted, they can suddenly snap, releasing energy in a spectacular explosion. This process not only lights up the sun's atmosphere, but also sends shockwaves of energy and particles hurtling through space. It's a reminder of just how powerful and unpredictable our star can be. As we continue, we'll explore how these explosive events travel through space and what happens when they reach Earth. But for now, picture the sun as a cosmic powerhouse, its surface alive with magnetic storms and bursts of energy that shape the very fabric of our solar system. Now, let's peel back the layers of a solar flare and examine its intricate anatomy. At the heart of these explosive events lies the sun's corona, the outermost layer of its atmosphere. This shimmering halo of superheated gas, visible during a total solar eclipse, is where solar flares originate. The corona is a chaotic realm, with temperatures soaring to millions of degrees, far hotter than the sun's surface. It's here that magnetic loops, vast arcs of magnetic fields, rise and twist like colossal ribbons, channeling energy and shaping the flare's structure. These magnetic loops are the backbone of a solar flare, acting as conduits for the immense energy stored within the sun's magnetic fields. When these fields become too tangled, They snap and reconnect in a process called magnetic reconnection, releasing energy in a dazzling burst. This energy takes the form of light, radiation, and charged particles, which surge outward into space. The light emitted during a flare spans the electromagnetic spectrum, from visible light to X-rays, creating a brilliant flash that can outshine the sun's normal output. Surrounding these magnetic loops is plasma, a state of matter where atoms are stripped of their electrons, creating a sea of charged particles. This plasma is not static. It flows and swirls, driven by the sun's magnetic fields. During a flare, the plasma is heated to extreme temperatures, causing it to expand and erupt, propelling energy and particles into the void of space. The energy released during a solar flare doesn't just vanish into the cosmos. It travels outward in waves, carried by the solar wind, a stream of charged particles that flows continuously from the sun. These particles, along with the radiation and light, race through space at incredible speeds, sometimes reaching Earth in just a matter of hours. When they arrive, they interact with our planet's magnetic field, setting off a chain of events that can disrupt technology and even pose risks to astronauts. As we move forward, we'll explore how these charged particles and radiation make their journey from the sun to Earth, and what happens when they collide with our planet's defenses. But for now, picture the sun's corona as a stage, where magnetic loops and plasma perform a cosmic dance, unleashing energy that shapes the solar system and beyond. Now, let's step back in time to explore some of the most significant solar flares in history, events that remind us of the sun's immense power and its potential to disrupt life on Earth. One of the most famous examples is the Carrington Event of 1859, named after the British astronomer Richard Carrington, who witnessed the solar flare that triggered it. This event was so intense that it caused telegraph systems across Europe and North America to fail. Operators reported sparks flying from their equipment, and some even found they could send messages without power, as the geomagnetic storm induced by the flare created electrical currents strong enough to operate the telegraphs. The Carrington Event wasn't just a scientific curiosity. It was a wake-up call. At the time, telegraphs were the cutting-edge technology of the day, much like our modern communication systems. The disruption caused by the flare highlighted how vulnerable even the most advanced technology of the time could be to solar activity. Imagine if a similar event occurred today, with our reliance on satellites, power grids, and global communication networks. The consequences could be far more severe. Another notable event took place in 1989, when a powerful geomagnetic storm caused by a solar flare knocked out power across Quebec, Canada, leaving millions in the dark for hours. This incident demonstrated how modern infrastructure, particularly power grids, remain susceptible to the effects of solar activity. Transformers overheated, and the entire grid was overwhelmed by the surge of electrical currents induced by the storm. These historical events serve as stark reminders of the sun's potential to disrupt our way of life. While the technology of the past was simpler, the impact of solar flares was still profound. Today, with our interconnected world and reliance on technology, the stakes are even higher. The lessons from these events underscore the importance of understanding and preparing for the risks posed by solar activity. As we reflect on these historical solar flares, it's clear that the sun's influence extends far beyond light and warmth. It has the power to shape our technological landscape, reminding us of the delicate balance between human innovation and the forces of nature. With this in mind, let's turn our attention to the sun's solar cycle and how its periodic changes influence the frequency and intensity of solar flares. Now, as we shift our gaze to the rhythm of the sun itself, let's explore the fascinating phenomenon known as the solar cycle. This cycle, which lasts approximately 11 years, is a natural pattern of rising and falling solar activity that governs the behavior of our star. During this cycle, the sun transitions between periods of high activity, called solar maximum, and periods of relative calm, known as solar minimum. At solar maximum, the sun becomes a hive of activity. Sunspots, dark, cooler regions on the sun's surface, multiply, and solar flares and coronal mass ejections become more frequent and intense. These explosive events are driven by the sun's tangled magnetic fields, which snap and reconnect, releasing vast amounts of energy. It's during this phase that the sun's influence on Earth is most pronounced, as heightened solar activity can lead to more frequent geomagnetic storms and disruptions to our technology. In contrast, solar minimum is a quieter time. Sunspots are fewer, and solar flares are less common. The sun's surface appears calmer, and its impact on Earth diminishes. However, even during solar minimum, the sun isn't entirely dormant. Smaller flares and occasional bursts of activity can still occur, reminding us that the sun is always active, even in its quieter phases. The solar cycle isn't just a scientific curiosity. It's a critical factor in understanding space weather and its effects on Earth. During solar maximum, the increased likelihood of solar flares and geomagnetic storms poses greater risks to satellites, power grids, and communication systems. Conversely, solar minimum offers a respite, but it also serves as a reminder that the sun's activity is cyclical and unpredictable. This ebb and flow of solar activity has been observed for centuries, with records of sunspots dating back to ancient times. Today, scientists use advanced tools like satellites and ground-based observatories to monitor the solar cycle, helping us predict periods of heightened activity and prepare for their potential impacts. As we consider the sun's solar cycle, it's clear that this rhythmic dance of activity and calm plays a crucial role in shaping our technological world. The cycle reminds us that the sun is not a static entity, but a dynamic force, constantly changing and influencing life on Earth. With this understanding, let's now turn our attention to how solar flares travel through space and the journey they take to reach our planet. Now, as we follow the path of these powerful solar flares, let's explore how they make their way from the sun to Earth. The journey begins with the sun's magnetic field, which plays a crucial role in shaping and propelling these bursts of energy. When a solar flare erupts, it sends a surge of charged particles, primarily electrons and protons, hurtling into space. These particles are carried by the solar wind, a continuous stream of plasma that flows outward from the sun in all directions. The solar wind acts like a cosmic conveyor belt, transporting the charged particles across the vast expanse of space. As these particles travel, they interact with the sun's magnetic field, which extends far beyond the star itself, creating a complex web of magnetic forces. This field guides the particles, accelerating them and shaping their trajectory as they move toward Earth. As the solar wind and its charged particles approach our planet, they encounter Earth's magnetosphere, a protective bubble created by our planet's own magnetic field. This magnetosphere acts as a shield, deflecting most of the harmful particles and radiation. However, during intense solar activity, such as a powerful solar flare or coronal mass ejection, the sheer volume and energy of the particles can overwhelm this defense. When this happens, the charged particles from the solar flare penetrate the magnetosphere, triggering a series of interactions. These particles spiral along Earth's magnetic field lines, funneling toward the poles. This process creates the stunning auroras we see in the night sky, but it also has more serious consequences. The influx of charged particles can induce electric currents in the upper atmosphere, which can then affect power grids, satellites, and communication systems on the ground. Understanding this journey is key to grasping how solar flares impact our planet. The interplay between the sun's magnetic field, the solar wind, and Earth's magnetosphere highlights the delicate balance that protects us from the sun's most extreme outbursts. Yet, as we'll see next, even this intricate system has its limits, especially when faced with the immense power of a major solar flare. Now, as we delve deeper into the protective mechanisms of our planet, let's turn our attention to Earth's magnetosphere, our first line of defense against the sun's relentless energy. This invisible shield, generated by Earth's magnetic field, extends tens of thousands of kilometers into space, wrapping our planet in a protective cocoon. It's this magnetosphere that stands between us and the constant barrage of charged particles streaming from the sun. The magnetosphere works like a cosmic umbrella, deflecting the majority of harmful solar radiation and charged particles away from Earth. When the solar wind, a flow of charged particles from the sun, reaches our planet, it encounters this magnetic barrier. Most of these particles are redirected around Earth, flowing harmlessly along the edges of the magnetosphere. This process not only protects us, but also shapes the magnetosphere into a teardrop-like structure, with a long tail stretching away from the sun. However, the magnetosphere isn't invincible. During periods of intense solar activity, such as a powerful solar flare or coronal mass ejection, the sheer force and volume of charged particles can overwhelm this natural defense. When this happens, some particles manage to penetrate the magnetosphere, particularly near the polar regions where the magnetic field lines converge. This intrusion can lead to spectacular auroras, but it also has more serious implications. The influx of charged particles can induce electric currents in the upper atmosphere, which can then cascade down to the surface, affecting power grids, communication systems, and even satellites. In extreme cases, these geomagnetic disturbances can cause widespread disruptions, highlighting the delicate balance between the sun's energy and Earth's protective shield. Understanding the magnetosphere's role is crucial to appreciating how vulnerable our modern technology can be to solar activity. While this natural barrier does an incredible job of shielding us, it's not foolproof. As we'll explore next, when the sun unleashes its full fury, even our planet's defenses can be pushed to their limits. Now, as we shift our focus to the aftermath of solar flares, let's explore the phenomenon of geomagnetic storms. These storms are essentially disturbances in Earth's magnetosphere, triggered when a massive influx of charged particles from the sun collides with our planet's magnetic field. This collision occurs when a solar flare, or coronal mass ejection, sends a surge of energy and particles hurtling toward Earth, overwhelming the magnetosphere's usual defenses. When these charged particles interact with Earth's magnetic field, they create intense electric currents that ripple through the upper atmosphere. These currents can distort the magnetosphere, causing it to fluctuate and vibrate like a giant cosmic drum. This distortion is what we call a geomagnetic storm. While the process might sound abstract, its effects are anything but. One of the most visible consequences of a geomagnetic storm is the appearance of auroras, those stunning displays of light in the polar skies. These occur when charged particles funnel along Earth's magnetic field lines and collide with gases in the atmosphere, releasing energy in the form of colorful light. While auroras are breathtaking, they are also a sign of the storm's power and its potential to disrupt the technology we rely on every day. For instance, geomagnetic storms can induce powerful electric currents in power grids. These currents, known as geomagnetically induced currents, can overload transformers and other critical infrastructure, leading to widespread blackouts. A famous example is the Quebec blackout of 1989, when a geomagnetic storm caused a massive power outage that left millions in the dark for hours. Communication systems are also vulnerable. High-frequency radio signals, which bounce off the ionosphere to travel long distances, can be disrupted as the ionosphere becomes ionized by the storm's energy. This can interfere with aviation, maritime, and emergency communications, creating potentially dangerous situations. Satellites, too, are at risk. The increased radiation and charged particles during a geomagnetic storm can damage sensitive electronics, disrupt signals, and even alter the orbits of satellites. This can impact everything from GPS navigation to weather forecasting, highlighting just how interconnected our modern world is with the space environment. In essence, geomagnetic storms are a stark reminder of the sun's immense power and its ability to influence life on Earth. While our magnetosphere provides a crucial defense, it's not impervious to the sun's fury. As we continue to rely on technology that's increasingly sensitive to space weather, understanding and preparing for these storms becomes more important than ever. With this in mind, let's now turn our attention to how these geomagnetic disturbances specifically impact satellites, the unsung heroes of our modern technological infrastructure. Now, as we delve deeper into the vulnerabilities of our modern infrastructure, let's focus on the impact of solar flares and geomagnetic storms on satellites. These orbiting marvels are the backbone of global communication, navigation, and weather forecasting, yet they are highly susceptible to the sun's unpredictable outbursts. When a solar flare or coronal mass ejection sends a surge of charged particles toward Earth, satellites are among the first to feel the effects. These particles can penetrate the outer layers of a satellite, damaging sensitive electronics and disrupting their operations. For example, in 2003, a powerful solar flare caused the failure of Japan's advanced Earth observing satellite, crippling its ability to monitor environmental changes. One of the most critical risks is the buildup of static electricity on a satellite surface. As charged particles bombard the satellite, they can create electrical discharges that fry circuits and render the equipment useless. This phenomenon, known as deep dielectric charging, has been responsible for numerous satellite malfunctions over the years. Navigation systems, particularly those relying on the global positioning system, are especially vulnerable. Satellites in the GPS constellation orbit at altitudes where they are exposed to higher levels of radiation during solar storms. In 2006, a geomagnetic storm caused temporary disruptions to GPS signals, leading to inaccuracies in navigation for aviation and maritime industries. Weather forecasting satellites are also at risk. These satellites provide critical data for predicting storms, tracking climate patterns, and monitoring natural disasters. When solar activity interferes with their sensors or communication systems, it can delay the transmission of vital information, potentially putting lives at risk. Perhaps one of the most dramatic examples occurred in 1994, when a geomagnetic storm caused the complete failure of Canada's Anik E-1 and E-2 communication satellites. The satellites were left spinning out of control, cutting off communication services for millions of people and costing hundreds of millions of dollars in damages and repairs. The challenges don't end there. Solar storms can also alter the orbits of satellites by heating the upper atmosphere, causing it to expand. This increased drag can pull satellites out of their intended paths, requiring costly adjustments to keep them operational. In essence, satellites are both a testament to human ingenuity and a reminder of our vulnerability to the sun's power. As we continue to rely on these technologies for everything from global communication to disaster response, understanding and mitigating the risks posed by solar activity becomes increasingly critical. With this in mind, let's now explore how these disruptions extend beyond satellites, affecting the very systems that guide our daily lives, starting with the global positioning system. Now turning to the intricate web of navigation systems that guide our modern world, let's examine how solar flares can disrupt the global positioning system, or GPS. This technology, which we often take for granted, is a cornerstone of industries ranging from aviation to shipping, and even everyday activities like driving and hiking. Yet, its reliance on satellites makes it highly susceptible to the sun's unpredictable behavior. When a solar flare or coronal mass ejection sends a surge of charged particles toward Earth, these particles can interfere with the signals transmitted between GPS satellites and ground receivers. The result: inaccuracies in positioning data, or, in extreme cases, complete signal loss, For industries that depend on precise navigation, even a minor disruption can have significant consequences. Take aviation, for example. Pilots rely on GPS for everything from takeoff and landing to navigating through crowded airspace. A solar storm-induced GPS malfunction could force planes to revert to older, less precise navigation methods, increasing the risk of delays, rerouting, or even accidents. In 2015, a solar storm caused temporary GPS disruptions over the North Pole, forcing airlines to alter flight paths and avoid the affected region altogether. The shipping industry faces similar challenges. Modern cargo ships use GPS to navigate vast oceans, ensuring they stay on course and avoid hazards like reefs or icebergs. A loss of GPS signals during a solar storm could leave ships adrift, relying on outdated charts and manual navigation techniques. This not only increases the risk of accidents, but also delays the delivery of goods, disrupting global supply chains. Even on land, the impact is felt. Emergency services, such as ambulances and fire trucks, rely on GPS to reach their destinations quickly. A solar-induced GPS failure could slow response times, putting lives at risk. Similarly, industries like agriculture, which use GPS for precision farming, could face setbacks in planting and harvesting schedules, affecting food production. The implications extend beyond immediate disruptions. Over time, repeated exposure to solar activity can degrade the performance of GPS satellites, shortening their operational lifespans and increasing the cost of maintaining the system. This creates a ripple effect, as governments and private companies must invest in more robust satellites and backup systems to ensure reliability. In essence, the disruption of GPS systems by solar flares is a stark reminder of how interconnected and vulnerable our modern infrastructure truly is. As we continue to rely on these technologies for critical operations, understanding and mitigating the risks posed by solar activity becomes not just a scientific challenge, but a necessity for safeguarding our way of life. With this in mind, let's now explore how these disruptions extend further, affecting the very power grids that keep our cities running. Now shifting our focus to the ground beneath our feet, let's delve into how solar flares can threaten the very backbone of modern civilization, our power grids. These vast networks, which deliver electricity to homes, businesses, and critical infrastructure, are surprisingly vulnerable to the sun's outbursts. When a solar flare or coronal mass ejection sends a wave of charged particles toward Earth, it doesn't just disrupt satellites, it can also wreak havoc on power systems, potentially plunging entire regions into darkness. The key to understanding this lies in the way geomagnetic storms interact with Earth's magnetic field. As these storms intensify, they induce powerful electric currents in the ground, known as geomagnetically induced currents, or GIC. These currents can flow into power lines and transformers, overwhelming their capacity and causing them to fail. The result: widespread blackouts that can last for hours, days, or even longer, depending on the severity of the storm and the resilience of the grid. A stark example of this occurred in March 1989, when a massive solar storm triggered a geomagnetic disturbance that crippled Quebec's power grid. Within seconds, the entire province was plunged into darkness, leaving millions without electricity for over 9 hours. The event caused widespread chaos, shutting down schools, businesses, and transportation systems, and costing the economy hundreds of millions of dollars. What made this incident particularly alarming was how quickly it unfolded, a reminder that even a single solar storm can bring a modern society to its knees. The Quebec blackout wasn't just a wake-up call for Canada. It highlighted a global vulnerability. Power grids in other regions, including the United States and Europe, also experienced disruptions during the same event, though on a smaller scale. This underscores the interconnected nature of modern energy systems and the potential for a single solar storm to trigger cascading failures across continents. The risks are even greater today, as our reliance on electricity has grown exponentially. From hospitals and water treatment plants to communication, networks, and financial systems, nearly every aspect of modern life depends on a stable power supply. A prolonged blackout caused by a severe solar storm could disrupt food distribution, compromise emergency services, and even threaten national security. To make matters worse, the aging infrastructure of many power grids increases their susceptibility to geomagnetic storms. Transformers, which are critical components of the grid, are particularly vulnerable. These massive devices are expensive and time-consuming to replace, and a widespread failure could leave entire regions without power for months. Efforts to mitigate these risks are underway, with some countries investing in technologies to shield their grids from solar-induced currents. However, progress has been slow, and many regions remain unprepared for a large-scale event. This raises urgent questions about how we can better protect our power systems and ensure the lights stay on, even in the face of the sun's fury. As we consider the fragility of our power grids, it's clear that the threat posed by solar flares extends far beyond the skies. It's a challenge that demands not only scientific innovation, but also global cooperation and proactive planning. With this in mind, let's now explore how these disruptions ripple further, affecting the very systems that keep us connected. Now turning to the invisible threads that keep our world connected, let's explore how solar flares can sever the lifelines of communication. Radio waves, which carry signals for aviation, emergency services, and military operations, are especially vulnerable to the sun's outbursts. When a solar flare erupts, it sends a burst of energy and charged particles hurtling toward Earth, creating disturbances in the ionosphere, a layer of the atmosphere crucial for radio communication. The ionosphere acts like a mirror, reflecting radio waves back to Earth and enabling long-distance communication. However, during a solar storm, this layer becomes unstable. The influx of energy from the flare ionizes the upper atmosphere, causing it to swell and distort. This phenomenon, known as ionospheric disturbance, can scatter or absorb radio signals, leading to communication blackouts. High-frequency radio systems, which rely on the ionosphere to bounce signals over long distances, are particularly affected. For aviation, this disruption can be catastrophic. Pilots depend on high-frequency radio to communicate with air traffic control, especially over oceans or remote areas where other forms of communication are unavailable. A sudden loss of contact could force planes to reroute or even ground flights, creating chaos in global air travel. Emergency services, too, rely on these systems during disasters when other networks may fail. A solar-induced communication breakdown could delay rescue operations, putting lives at risk. The military faces similar challenges. Secure, reliable communication is essential for coordinating operations, and disruptions could compromise missions or even national security. During the Cold War, for example, solar storms were known to interfere with military radar systems, creating false signals that could be mistaken for enemy activity. Today, the stakes are even higher, as modern warfare increasingly depends on real-time communication and satellite-based technologies. The science behind these disruptions lies in the way solar particles interact with Earth's magnetic field. As the particles collide with the ionosphere, they create turbulence, much like ripples on a pond. This turbulence can cause radio signals to fade, distort, or disappear entirely. The severity of the disruption depends on the strength of the solar flare and the density of the ionosphere at the time. Interestingly, not all radio frequencies are affected equally. While high-frequency systems bear the brunt of the disruption, very low-frequency and ultra-low-frequency signals, used for submarine communication and some scientific research, can actually be enhanced during a solar storm. This is because these signals travel through the lower layers of the ionosphere, which become more conductive under the influence of solar particles. Despite these nuances, the overall impact of solar flares on communication systems is a cause for concern. As our reliance on wireless technology grows, so does our vulnerability to space weather. Efforts to mitigate these risks include developing more resilient communication technologies and improving space weather forecasting. However, much like the challenges facing power grids, progress has been uneven, and many systems remain at risk. As we reflect on the fragility of our communication networks, it's clear that solar flares pose a multifaceted threat. From aviation to emergency response, the ripple effects of a single solar storm can disrupt the very systems that keep us connected. With this in mind, let's now shift our focus to the skies above, where another critical aspect of modern life hangs in the balance. As we venture beyond Earth's protective atmosphere, the dangers posed by solar flares become even more pronounced. Space exploration, while a testament to human ingenuity, faces unique vulnerabilities when it comes to the sun's unpredictable outbursts. Astronauts, spacecraft, and even the International Space Station are exposed to heightened risks during solar storms, making this a critical area of concern for space agencies worldwide. One of the most immediate threats to astronauts is increased radiation exposure. Solar flares unleash bursts of high-energy particles, including protons and electrons, which can penetrate spacecraft shielding. Prolonged exposure to this radiation can lead to serious health risks, such as an increased likelihood of cancer, damage to the central nervous system, and even acute radiation sickness. For missions beyond low Earth orbit, such as those to the Moon or Mars, the lack of Earth's magnetosphere leaves astronauts even more exposed, making radiation protection a top priority. Spacecraft electronics are equally at risk. The charged particles from solar flares can interfere with onboard systems, causing malfunctions or even permanent damage. Sensitive instruments, such as navigation systems, communication devices, and scientific equipment, are particularly susceptible. A single solar storm could disrupt a mission's critical operations, jeopardizing years of planning and billions of dollars in investment. To mitigate these risks, space agencies have developed a range of strategies. One approach is to design spacecraft with enhanced shielding, using materials that can absorb or deflect harmful radiation. For example, the International Space Station is equipped with specialized shielding in its crew modules, providing a safer environment for astronauts during solar events. Additionally, mission planners carefully monitor space weather forecasts to schedule launches and spacewalks during periods of low solar activity, reducing the likelihood of exposure to solar storms. Another key strategy is the use of early warning systems. Satellites like the Solar and Heliospheric Observatory and the Deep Space Climate Observatory provide real-time data on solar activity, allowing ground teams to alert astronauts and take protective measures. In some cases, astronauts may be instructed to move to more heavily shielded areas of the spacecraft until the storm passes. Despite these precautions, the challenge of protecting astronauts and spacecraft from solar flares remains significant. As humanity sets its sights on deeper space exploration, such as missions to Mars, the need for advanced radiation shielding and more accurate space weather forecasting becomes even more urgent. Innovations in materials science, artificial intelligence, and space weather modeling are paving the way for safer journeys, but the risks are far from eliminated. The interplay between solar flares and space exploration underscores the delicate balance between ambition and caution. While the stars beckon, the sun's unpredictable nature serves as a reminder of the challenges that lie ahead. As we continue to push the boundaries of human exploration, understanding and mitigating the dangers of solar activity will remain a cornerstone of our journey into the cosmos. With this in mind, let's now turn our attention to the broader economic implications of solar flares, exploring how these cosmic events could ripple through global markets and industries. Now shifting our focus to the ground, let's explore how a massive solar flare could ripple through the global economy, affecting everything from trade to financial markets. The interconnected nature of modern technology means that a disruption in one area can quickly cascade into others, creating a domino effect with far-reaching consequences. One of the most immediate impacts would be on global trade. Shipping and logistics rely heavily on satellite-based navigation systems, such as GPS, to coordinate the movement of goods across the world. A solar flare-induced geomagnetic storm could disrupt these systems, causing delays, misrouted shipments, and even accidents. Ports, which depend on precise timing and coordination, could grind to a halt, leading to bottlenecks in supply chains. Industries like manufacturing, agriculture, and retail, which rely on just-in-time delivery systems, would face significant disruptions, potentially leading to shortages of essential goods and skyrocketing prices. Financial markets are equally vulnerable. Stock exchanges, banks, and trading platforms depend on high-speed communication, networks, and satellite links to function. A major solar flare could knock out these systems, halting trading and causing chaos in global markets. The 2010 flash crash, where a technical glitch caused a temporary market collapse, offers a glimpse of what could happen on a much larger scale. Investors might panic, leading to massive sell-offs and economic instability. The ripple effects could extend to pensions, savings, and even national economies, as governments scramble to stabilize the situation. Supply chains, already strained by recent global events, would face unprecedented challenges. Solar flares could damage critical infrastructure, such as power grids and communication networks, disrupting the flow of raw materials and finished products. For example, a blackout caused by a geomagnetic storm could shut down factories, leaving manufacturers unable to meet demand. The automotive industry, which relies on a complex web of suppliers, could see production lines grind to a halt, while the tech sector might face shortages of semiconductors and other key components. The economic consequences of a massive solar flare event would not be limited to immediate disruptions. The long-term effects could include reduced consumer confidence, increased insurance premiums, and higher costs for businesses as they invest in protective measures. Governments might need to allocate significant resources to rebuild infrastructure and support affected industries, diverting funds from other critical areas like healthcare and education. What makes this scenario particularly concerning is the interconnectedness of modern technology. A single point of failure, such as a damaged satellite or a downed power grid, can trigger a chain reaction that affects multiple sectors. This interdependence highlights the need for robust contingency plans and investments in resilient infrastructure. As we consider the economic fallout of a solar flare event, it's clear that the stakes are high. The global economy, built on a foundation of advanced technology, is both a marvel of human achievement and a potential vulnerability. Understanding these risks is the first step toward mitigating them, ensuring that we can weather the storm both literally and figuratively when the sun next unleashes its fury. With this in mind, let's now turn our attention to the health risks posed by solar radiation, examining how increased exposure could affect not just astronauts, but people on Earth as well. Now shifting our focus to the skies and beyond, let's explore how solar flares and the radiation they unleash could pose significant health risks to humans, both on Earth and in space. While we often think of solar flares as a threat to technology, their impact on living organisms is equally concerning, especially for those who spend time at high altitudes or venture beyond our planet's protective atmosphere. For astronauts, the dangers are particularly acute. Outside Earth's magnetosphere, they are exposed to much higher levels of solar radiation, which can damage cells and increase the risk of cancer, cataracts, and other health issues. Even inside spacecraft, shielding can only offer limited protection during intense solar events. Prolonged exposure to this radiation could have serious long-term consequences, making it a critical challenge for future missions to the Moon, Mars, and beyond. But it's not just astronauts who are at risk. Frequent flyers, such as pilots and airline passengers, are also exposed to elevated levels of cosmic and solar radiation, especially during long-haul flights at high altitudes. While the doses are much lower than in space, repeated exposure over time can still pose health risks, particularly for those who fly regularly. Studies have shown that flight crews, for example, have a slightly higher risk of certain cancers compared to the general population, likely due to their increased exposure to radiation. On the ground, the risks are lower but not negligible. During a major solar flare event, radiation levels on Earth can spike, particularly in regions near the poles where the magnetosphere is weaker. While our atmosphere provides significant protection, those living in high-altitude areas or working in certain industries, such as aviation or telecommunications, may face slightly higher exposure. Over time, even small increases in radiation can contribute to health issues, making it important to monitor and mitigate these risks. The long-term effects of radiation exposure are another area of concern. Beyond the immediate risks of acute exposure, such as radiation sickness, chronic exposure to low levels of radiation can lead to DNA damage, increasing the likelihood of cancer and other diseases. This is why space agencies and health organizations are investing in research to better understand these risks and develop strategies to protect both astronauts and the general public. As we continue to push the boundaries of exploration and rely more heavily on technology, understanding the health risks posed by solar radiation becomes increasingly important. By studying these effects and developing protective measures, we can ensure that humanity is better prepared to face the challenges of a dynamic and sometimes unpredictable sun. With this in mind, let's now turn our attention to the relationship between solar activity and Earth's climate, exploring whether solar flares could influence global temperatures or weather patterns, and debunking some common myths along the way. Now shifting our gaze to Earth's climate, let's explore the intriguing connection between solar flares and our planet's weather patterns. While solar flares are often associated with technological disruptions, their potential impact on climate has sparked curiosity and debate. Could these explosive events from the sun influence global temperatures or even alter weather systems? The answer is more nuanced than you might think. Solar flares release immense amounts of energy, including ultraviolet light and X-rays, which can temporarily affect Earth's upper atmosphere. However, the idea that solar flares directly cause significant changes in global temperatures or weather patterns is largely a myth. The energy from a single flare, while powerful, is minuscule compared to the vast energy systems driving Earth's climate. For example, the total energy output of the sun remains relatively stable over short periods, and even during periods of heightened solar activity, the fluctuations are too small to cause noticeable shifts in global temperatures. That said, solar activity does play a role in shaping certain atmospheric processes. During periods of high solar activity, such as the solar maximum, increased ultraviolet radiation can heat the upper layers of the atmosphere, known as the thermosphere. This can lead to slight expansions of the atmosphere, which may influence satellite orbits and communication systems. However, these effects are localized and do not translate into significant changes in weather patterns or long-term climate trends. One common misconception is that solar flares are responsible for extreme weather events, such as hurricanes or heat waves. In reality, these phenomena are driven by complex interactions within Earth's atmosphere and oceans, not by solar activity. While the sun's energy is the ultimate source of Earth's climate system, the direct influence of solar flares on day-to-day weather is negligible. Another myth worth debunking is the idea that solar flares could reverse or halt climate change. While the sun's natural cycles do cause slight variations in solar irradiance, these changes are far too small to counteract the rapid warming caused by human activities, such as burning fossil fuels and deforestation. In fact, studies show that the sun's influence on global temperatures over the past century has been minimal compared to the impact of greenhouse gas emissions. So, while solar flares are fascinating and powerful events, their influence on Earth's climate is limited. They remind us of the sun's dynamic nature, but when it comes to shaping our planet's weather and long-term climate, Earth's own systems play a far more significant role. Understanding this distinction helps us focus on the real drivers of climate change and the steps we can take to address them. With this clearer picture of solar flares and climate, let's now turn to the tools and techniques scientists use to monitor solar activity and predict these explosive events, shedding light on how we stay one step ahead of the sun's unpredictable behavior. Now, as we venture into the realm of prediction, let's uncover how scientists keep a watchful eye on the sun's fiery temper. Predicting solar flares is no small feat, but thanks to cutting-edge technology and relentless observation, we've made significant strides in understanding and anticipating these explosive events. At the heart of this effort are specialized satellites designed to monitor the sun's activity around the clock. Two of the most critical tools in this mission are the Solar and Heliospheric Observatory, known as SOHO, and the Solar Terrestrial Relations Observatory, or STEREO. These satellites work tirelessly to capture detailed images and data of the sun's surface, magnetic fields, and solar wind. SOHO, for instance, has been a game changer since its launch in the late 1990s, providing unprecedented insights into solar dynamics. Meanwhile, STEREO's unique dual spacecraft setup allows scientists to view the sun from multiple angles, offering a more comprehensive picture of solar activity. But monitoring the sun is only part of the challenge. Predicting solar flares requires analyzing vast amounts of data to identify patterns and precursors. Scientists look for signs like sunspots, which are dark, cooler regions on the sun's surface caused by intense magnetic activity. These sunspots often serve as the birthplace of solar flares, and their size, complexity, and magnetic configuration can hint at the likelihood of an eruption. Despite these advancements, accurate forecasting remains a daunting task. The sun's behavior is inherently chaotic, and even the most sophisticated models struggle to predict exactly when and where a flare will occur. One major hurdle is the sheer complexity of the sun's magnetic fields, which can twist, tangle, and snap in unpredictable ways. Additionally, while we can observe the sun's surface, much of the magnetic activity that drives flares happens beneath it, hidden from direct view. Another challenge lies in the speed at which solar flares develop. Some flares can erupt in a matter of minutes, leaving little time for warning. This rapid onset makes it difficult to provide timely alerts, especially for industries and systems that rely on precise forecasts, such as aviation and satellite operations. Yet, despite these obstacles, scientists continue to refine their methods. Advances in artificial intelligence and machine learning are opening new doors, enabling researchers to analyze data more efficiently and identify subtle patterns that might otherwise go unnoticed. These technologies hold the promise of more accurate and timely predictions, helping us better prepare for the sun's next outburst. As we look to the future, the quest to predict solar flares remains a fascinating and vital endeavor. It's a reminder of how much we've learned about our star and how much more there is to discover. With each new breakthrough, we move closer to understanding the sun's mysteries and safeguarding our technology-driven world from its unpredictable power. With this glimpse into the science of solar flare prediction, let's now explore how early warning systems are being developed to give us a heads up when the sun decides to unleash its fury. Now, as we shift our focus to the critical role of early warning systems, let's explore how humanity is working to stay one step ahead of the sun's unpredictable outbursts. Early warning systems for solar flares and geomagnetic storms are essential tools in our efforts to protect modern technology and infrastructure. These systems rely on a combination of advanced technology, international collaboration, and real-time data analysis to provide timely alerts when solar activity threatens Earth. At the forefront of these efforts are organizations like the National Oceanic and Atmospheric Administration, or NOAA, and the National Aeronautics and Space Administration, known as NASA. NOAA Space Weather Prediction Center plays a pivotal role in monitoring solar activity and issuing alerts to governments, industries, and the public. Using data from satellites like the Solar and Heliospheric Observatory and the Solar Terrestrial Relations Observatory, NOAA tracks sunspots, solar flares, and coronal mass ejections, providing forecasts that help mitigate potential disruptions. NASA, on the other hand, focuses on understanding the science behind solar activity. Missions like the Parker Solar Probe and the Solar Dynamics Observatory provide invaluable data about the sun's magnetic fields, solar wind, and flare dynamics. This information not only enhances our ability to predict solar events, but also improves the accuracy of early warning systems. One of the key challenges in developing these systems is the need for speed and precision. Solar flares and geomagnetic storms can impact Earth within minutes to hours, leaving little time for preparation. To address this, scientists have developed algorithms that analyze real-time data to detect early signs of solar activity. These algorithms can identify patterns, such as the rapid growth of sunspots or the sudden release of energy that often precede a flare or storm. Another critical component of early warning systems is international cooperation. Solar activity is a global concern, and no single country can tackle it alone. Organizations like the International Space Environment Service bring together scientists and institutions from around the world to share data, resources, and expertise. This collaborative approach ensures that early warnings are as accurate and widespread as possible, benefiting everyone on the planet. Despite these advancements, there's still room for improvement. Current systems can provide warnings, but they often lack the precision needed to predict the exact timing, location, and intensity of a solar event. This is where emerging technologies, such as artificial intelligence and machine learning, come into play. By analyzing vast amounts of historical and real-time data, these tools can help refine predictions and reduce uncertainties, giving us more time to prepare. As we continue to refine these systems, the goal is clear: to create a robust, reliable network that can provide early warnings with enough lead time to protect critical infrastructure, from power grids to satellites. The development of early warning systems is a testament to human ingenuity and our determination to safeguard our technology-driven world from the sun's unpredictable power. With this understanding of how early warning systems work, let's now turn our attention to the practical steps we can take to prepare for a major solar storm. Now, as we delve into the practical steps for preparing for a major solar storm, it's essential to recognize that preparedness is a shared responsibility. Governments, businesses, and individuals all have a role to play in minimizing the potential disruptions caused by solar flares and geomagnetic storms. The key lies in proactive planning, robust systems, and widespread awareness. For governments, the first line of defense is investing in resilient infrastructure. This includes upgrading power grids to withstand geomagnetic disturbances, ensuring that critical communication networks have backup systems, and establishing clear protocols for responding to solar storm alerts. Governments should also prioritize public education campaigns to inform citizens about the risks of solar activity and the steps they can take to protect themselves. Businesses, particularly those reliant on technology and global connectivity, must also take action. This means developing contingency plans for potential disruptions to satellite communications, GPS systems, and power supplies. Companies should consider diversifying their communication channels, investing in shielded electronics, and training employees to respond effectively during a solar storm. For industries like aviation, shipping, and finance, where precision and reliability are paramount, these measures are especially critical. On an individual level, preparation begins with awareness. Understanding the potential impacts of solar flares can help people take simple yet effective steps to safeguard their homes and families. For instance, having backup power sources like generators or solar panels can provide electricity during prolonged blackouts. Keeping emergency kits stocked with essentials such as food, water, and medical supplies is also a wise precaution. Additionally, staying informed through reliable sources like NOAA Space Weather Prediction Center ensures that individuals can act quickly when warnings are issued. Public awareness campaigns play a vital role in fostering a culture of preparedness. By educating communities about the science behind solar flares and their potential consequences, we can empower people to take proactive measures. Schools, media outlets, and community organizations can all contribute to spreading this knowledge, ensuring that everyone understands the importance of being ready for a solar storm. Another crucial aspect of preparation is collaboration. Governments, businesses, and individuals must work together to share information, resources, and best practices. International cooperation, as we've seen with organizations like the International Space Environment Service, is equally important. By pooling our collective expertise and efforts, we can build a more resilient global community, capable of weathering the sun's most intense outbursts. As we continue to advance our understanding of solar activity and improve our early warning systems, the importance of preparation cannot be overstated. While we may not be able to prevent solar flares, we can certainly reduce their impact through careful planning and collective action. By taking these steps today, we can ensure that our technology-driven world remains secure, even in the face of the sun's unpredictable power. With these strategies in mind, let's now explore how technology itself can be hardened to better withstand the effects of solar flares. Now, as we shift our focus to the technological front, let's explore how we can fortify our systems to better withstand the sun's unpredictable outbursts. Hardening technology against solar flares is not just a matter of innovation. It's a necessity in our increasingly interconnected world. One of the most effective strategies is shielding electronics from the intense radiation emitted during solar flares. This involves using materials that can absorb or deflect harmful particles, protecting sensitive components in everything from smartphones to satellites. For instance, spacecraft and satellites are often equipped with specialized shielding to minimize damage from solar radiation. On Earth, critical infrastructure like power stations and communication hubs can also benefit from similar protective measures, ensuring they remain operational even during extreme solar events. Another key approach is designing robust power grids capable of handling geomagnetic disturbances. Solar flares can induce powerful electric currents in power lines, potentially overloading transformers and causing widespread blackouts. To counter this, engineers are developing grids with built-in safeguards, such as automatic shut-off systems and surge protectors. These innovations can help prevent cascading failures, keeping the lights on even when the sun is at its most volatile. Satellites, which are particularly vulnerable to solar activity, require special attention. Developing radiation-resistant satellites is a growing field of research. By using advanced materials and redundant systems, engineers can create satellites that are less likely to fail during a solar storm. Additionally, incorporating artificial intelligence into satellite operations allows for real-time adjustments, such as reorienting solar panels or shutting down non-essential systems to conserve power during intense radiation bursts. Beyond hardware, software also plays a crucial role in hardening technology. Algorithms designed to detect and mitigate the effects of solar flares can help systems adapt quickly to changing conditions. For example, GPS networks can use error correction software to maintain accuracy even when solar activity disrupts signals. Similarly, communication systems can switch to alternative frequencies or protocols to avoid interference caused by ionospheric disturbances. Collaboration between industries and governments is essential to drive these advancements forward. By sharing knowledge and resources, we can accelerate the development of technologies that are not only resilient, but also cost-effective. International partnerships, like those seen in space exploration, can serve as a model for global cooperation in this critical area. As we continue to innovate, it's important to remember that hardening technology is an ongoing process. The sun's behavior is unpredictable, and our defenses must evolve alongside our understanding of solar activity. By investing in research, fostering collaboration, and prioritizing resilience, we can build a technological infrastructure capable of withstanding even the most powerful solar flares. With these advancements in mind, let's now turn to the role of artificial intelligence in predicting and mitigating the impact of solar flares, a frontier where cutting-edge technology meets the challenges of space weather. Now, as we step into the realm of cutting-edge technology, let's explore how artificial intelligence is revolutionizing our ability to predict and respond to solar flares. Artificial intelligence, or AI, is becoming an indispensable tool in the field of space weather forecasting, offering new ways to analyze vast amounts of data and anticipate the sun's behavior with greater accuracy. One of the most exciting applications of AI is its ability to process data from satellites and ground-based observatories in real time. By feeding this information into machine learning algorithms, scientists can identify patterns and anomalies that might signal an impending solar flare. For example, NASA's Solar Dynamics Observatory and other missions generate enormous datasets that would take humans years to analyze. AI, however, can sift through this data in minutes, flagging potential threats and helping forecasters issue timely warnings. Machine learning models are also being trained to predict the intensity and direction of solar flares. By studying historical data from past solar events, these models can learn to recognize the conditions that lead to powerful flares. This predictive capability is crucial for preparing for geomagnetic storms, as it allows governments and industries to take proactive measures, such as rerouting flights or temporarily shutting down vulnerable power grids. Innovative projects are pushing the boundaries of what AI can achieve in space weather forecasting. For instance, researchers are developing neural networks that can simulate the sun's magnetic field, providing insights into how solar flares form and evolve. These simulations not only improve our understanding of solar activity, but also help refine forecasting models, making them more reliable and precise. Another groundbreaking application is the use of AI to enhance satellite resilience. By integrating machine learning into satellite systems, engineers can create autonomous spacecraft capable of adjusting their operations during solar storms. For example, satellites can use AI to reorient their solar panels, shut down non-essential systems, or even reposition themselves to minimize radiation exposure. This level of adaptability is critical for maintaining communication, navigation, and weather monitoring services during extreme solar events. The potential of AI extends beyond prediction and mitigation. It also plays a key role in educating the public and raising awareness about solar flares. Interactive tools powered by AI can provide real-time updates on solar activity, helping people understand the risks and take appropriate precautions. These tools are particularly valuable for industries like aviation and shipping, where accurate information can mean the difference between safety and disaster. As we continue to harness the power of artificial intelligence, it's clear that this technology is transforming our approach to space weather. By combining AI with traditional forecasting methods, we can create a more resilient and informed society, better equipped to face the challenges posed by solar flares. With these advancements in mind, let's now turn to how solar flares have been portrayed in popular culture, exploring the intersection of science and storytelling in our understanding of these cosmic events. Now, as we shift our gaze from the scientific to the imaginative, let's explore how solar flares have captured the attention of storytellers and filmmakers, weaving their way into the fabric of popular culture. Solar flares, with their dramatic potential to disrupt life as we know it, have become a compelling plot device in movies, books, and television shows. These portrayals often blend scientific concepts with creative liberties, offering audiences a mix of awe, inspiring spectacle, and thought-provoking scenarios. One of the most iconic depictions of solar flares in cinema is the disaster film genre, where these cosmic events are often portrayed as apocalyptic triggers. Movies like The Day After Tomorrow and Knowing use solar flares as catalysts for global chaos, showcasing their ability to wreak havoc on Earth's infrastructure and climate. While these films take dramatic liberties, they do tap into a very real fear, the vulnerability of our technology-dependent world to solar activity. Television series have also explored the theme of solar flares, often using them as a backdrop for human drama and survival stories. For instance, in the series Revolution, a massive solar flare knocks out all electrical power, plunging the world into a pre-industrial state. This premise, while exaggerated, highlights the potential consequences of a prolonged blackout caused by a geomagnetic storm. It also raises questions about how society might adapt or collapse in the face of such a catastrophe. Books, too, have delved into the science and speculation surrounding solar flares. Science fiction novels like Lucifer's Hammer and Sevenev's imagine the aftermath of solar events, blending scientific accuracy with gripping narratives. These stories often explore not just the immediate effects of solar flares, but also the long-term societal and environmental changes they could bring. By grounding their plots in real scientific principles, authors create scenarios that feel both plausible and deeply unsettling. However, the line between fact and fiction can sometimes blur. While many portrayals of solar flares are rooted in real science, they often amplify the scale and immediacy of their effects for dramatic impact. For example, the idea of a solar flare instantly incinerating Earth's surface is a common trope, but in reality, the sun's radiation poses a more gradual threat to technology and infrastructure. This balance between scientific accuracy and storytelling is a delicate one, as creators aim to entertain while also educating their audiences. Interestingly, some works of fiction have even inspired real-world discussions about solar flare preparedness. Films and books that depict the consequences of solar storms have sparked public interest in space weather, prompting governments and organizations to invest in research and early warning systems. In this way, popular culture serves as both a mirror and a catalyst, reflecting our fears and driving us to address them. As we reflect on these portrayals, it's clear that solar flares hold a unique place in our collective imagination. They remind us of the delicate balance between our technological achievements and the forces of nature, offering a lens through which we can explore both our vulnerabilities and our resilience. With this blend of science and storytelling in mind, let's now turn to the lessons we can learn from historical solar flare events, examining how past experiences can guide our preparations for the future. Now, as we step back into the annals of history, let's uncover the lessons that past solar flare events have left behind. These moments, etched in time, serve as both warnings and guides, offering invaluable insights into how we might prepare for future solar storms. One of the most significant historical solar flare events occurred in September 1859, known as the Carrington Event, named after the astronomer Richard Carrington, who observed the solar flare that triggered it. This event remains the most powerful geomagnetic storm ever recorded. Telegraph systems across the globe failed, with operators reporting sparks flying from their equipment and even paper catching fire. In some cases, telegraphs continue to operate even after being disconnected from their power sources, powered solely by the energy of the geomagnetic storm. The Carrington Event serves as a stark reminder of the sun's potential to disrupt human technology. While the world of 1859 was far less dependent on electricity than today, the event still caused widespread chaos. Fast forward to the modern era, and the stakes are exponentially higher. A similar event today could cripple power grids, disrupt satellite communications, and bring global commerce to a standstill. Another notable event occurred in March 1989, when a geomagnetic storm caused by a solar flare plunged the entire province of Quebec, Canada, into darkness. The storm induced powerful electric currents in the power grid, overwhelming transformers and causing a blackout that lasted for 9 hours. Millions of people were left without power, and the economic impact was significant. This event highlighted the vulnerability of modern power infrastructure to solar activity and spurred efforts to better understand and mitigate these risks. These historical events teach us two critical lessons. First, they underscore the importance of monitoring solar activity. Advances in technology have given us tools like the Solar and Heliospheric Observatory and the Deep Space Climate Observatory, which provide real-time data on solar flares and geomagnetic storms. Early warning systems, developed by organizations like the National Oceanic and Atmospheric Administration and the National Aeronautics and Space Administration, allow us to anticipate and prepare for solar events. Second, they emphasize the need for robust infrastructure. Power grids, satellites, and communication systems must be designed to withstand the effects of geomagnetic storms. This includes implementing protective measures like surge protectors, grounding systems, and backup power supplies. Governments and industries must also develop contingency plans to ensure continuity of essential services during a solar storm. Beyond these practical measures, historical solar flare events remind us of the importance of public awareness. Educating people about the risks of solar activity and how to prepare for it can help mitigate panic and ensure a coordinated response. From emergency kits to communication plans, individual preparedness plays a crucial role in building societal resilience. As we look to the future, the lessons of the past serve as a foundation for progress. By studying historical solar flare events, we can better understand the sun's behavior, improve our technology, and strengthen our preparedness. These efforts are not just about protecting our infrastructure, they are about safeguarding our way of life. With these lessons in mind, let's now turn our attention to the future of solar activity, exploring what the sun's evolving behavior might mean for Earth in the years to come. As we gaze toward the horizon of our solar future, one question looms large: what lies ahead for the sun, and by extension, for us here on Earth? The sun, like all stars, is not a static entity. It undergoes changes over time, and these changes could have profound implications for solar activity, including the frequency and intensity of solar flares. The sun is currently in what scientists call the main sequence phase of its life cycle, a period during which it fuses hydrogen into helium in its core. This phase has lasted for about 4.6 billion years and is expected to continue for another 5 billion years or so. However, as the sun ages, its core will gradually deplete its hydrogen fuel, leading to changes in its structure and behavior. One of the key factors to consider is the sun's magnetic activity, which drives solar flares and other phenomena. Over the course of its 11-year solar cycle, the sun experiences periods of high and low activity, known as solar maximum and solar minimum. During solar maximum, the sun's magnetic field becomes more complex and dynamic, leading to an increase in sunspots, solar flares, and coronal mass ejections. As the sun ages, some scientists speculate that these cycles could become more pronounced, potentially leading to more frequent and intense solar flares. However, other research suggests that the sun's overall magnetic activity may decrease over time. As the sun exhausts its hydrogen fuel, its core will contract and heat up, causing its outer layers to expand and cool. This process, known as the red giant phase, could lead to a reduction in the sun's magnetic dynamo, the mechanism that generates its magnetic field. If this happens, solar flares and other forms of solar activity might become less frequent and less intense. The implications of these changes for Earth are significant. If solar flares become more frequent and powerful, the risks to our technology and infrastructure could increase. On the other hand, a decrease in solar activity might reduce these risks, but could also have other consequences, such as changes in Earth's climate. The sun's energy output plays a crucial role in regulating our planet's temperature, and any significant shifts in solar activity could influence global weather patterns. Another factor to consider is the sun's interaction with the broader galaxy. As the sun orbits the center of the Milky Way, it passes through regions of varying density and magnetic fields. These galactic environments could influence the sun's activity, potentially triggering periods of heightened or reduced solar flares. While predicting the exact future of solar activity is challenging, one thing is clear: continued observation and research are essential. By studying the sun's behavior over time, scientists can refine their models and improve their ability to forecast solar flares and other phenomena, This knowledge will be crucial for protecting our technology, infrastructure, and way of life in the decades and centuries to come. As we look ahead, the sun's future remains a fascinating and complex puzzle. Whether solar flares become more or less frequent, one thing is certain: our understanding of the sun and its impact on Earth will continue to evolve, guiding us toward a safer and more resilient future. With this glimpse into the sun's potential future, let's now explore how global cooperation is shaping our ability to monitor and respond to solar activity, ensuring that humanity is prepared for whatever the sun may bring. As we shift our focus to the broader picture, it becomes clear that the challenges posed by solar flares are not confined to any single nation or region. The need for global cooperation in monitoring and responding to space weather has never been more urgent. Solar flares and their effects on Earth's technology and infrastructure are a shared concern, requiring a unified approach to mitigate risks and protect our interconnected world. One of the most significant examples of international collaboration in this field is the partnership between the National Oceanic and Atmospheric Administration in the United States and the European Space Agency. Together, they operate satellites like the Solar and Heliospheric Observatory, or SOHO, and the Solar Orbiter, which provide critical data on solar activity. These missions allow scientists to track sunspots, solar flares, and coronal mass ejections in real time, offering early warnings that can help governments and industries prepare for potential disruptions. However, coordinating a global response to solar flares is not without its challenges. Different countries have varying levels of technological capability and resources, making it difficult to ensure that all nations are equally prepared. Additionally, the sheer scale of the problem requires seamless communication and data sharing across borders, which can be complicated by political, logistical, and technical barriers. Despite these challenges, progress is being made. Organizations like the International Space Environment Service, or ISES, bring together space weather experts from around the world to share data, develop forecasting models, and coordinate responses to solar events. This network of observatories and research institutions plays a vital role in improving our understanding of solar activity and its impacts on Earth. Another key aspect of global cooperation is the development of standardized protocols for responding to solar flares. For example, the International Civil Aviation Organization has established guidelines for airlines to follow during periods of heightened solar activity, helping to ensure the safety of passengers and crew. Similarly, power grid operators in different countries are working together to develop strategies for protecting infrastructure from geomagnetic storms. The importance of international collaboration extends beyond immediate preparedness. By pooling resources and expertise, the global community can advance research into solar physics, improve forecasting models, and develop new technologies to mitigate the effects of solar flares. This collective effort not only enhances our ability to respond to current threats, but also lays the groundwork for long-term resilience. As we look to the future, the need for global cooperation on space weather will only grow. With the increasing reliance on technology and the interconnected nature of our world, the stakes are higher than ever. By working together, nations can ensure that humanity is better prepared to face the challenges posed by solar flares and other space weather phenomena. With this understanding of the importance of international collaboration, let's now explore how solar flares might influence the search for extraterrestrial life, shedding light on the broader implications of solar activity beyond our own planet. As we venture beyond Earth, the implications of solar flares extend far beyond our own planet, raising intriguing questions about the search for extraterrestrial life. Solar activity, including flares and coronal mass ejections, plays a significant role in shaping the environments of other planets and moons, influencing their potential to support life. Consider Mars, for example. Unlike Earth, Mars lacks a strong magnetic field and a thick atmosphere, leaving it more vulnerable to the effects of solar radiation. Intense solar flares could strip away what little atmosphere the planet has, making it even more inhospitable. This raises important questions about whether life could have ever existed on Mars, or if it could survive there today. Similarly, moons like Europa and Enceladus, which are believed to have subsurface oceans, present another fascinating scenario. While these moons are shielded by thick layers of ice, solar flares could still impact their surfaces, potentially altering the chemistry of their icy shells. This, in turn, might affect the conditions within their hidden oceans, where scientists speculate life could exist. Even planets outside our solar system, known as exoplanets, are not immune to the effects of solar flares. Many of these planets orbit red dwarf stars, which are known for their frequent and intense solar activity. Flares from these stars could bombard nearby planets with harmful radiation, making it difficult for life to thrive unless those planets have protective magnetic fields or atmospheres. The study of solar flares also offers clues about the habitability of distant worlds. By observing how solar activity affects planets and moons in our own solar system, scientists can develop models to predict the conditions on exoplanets. This knowledge helps narrow down the search for potentially habitable worlds, guiding future missions and telescopes designed to detect signs of life. However, solar flares are not always a barrier to life. In some cases, they might even play a role in creating the conditions necessary for life to emerge. For instance, the energy from solar flares could drive chemical reactions on a planet's surface or in its atmosphere, potentially leading to the formation of complex molecules essential for life. As we continue to explore the cosmos, understanding the relationship between solar flares and habitability will be crucial. It not only informs our search for extraterrestrial life, but also deepens our appreciation for the delicate balance that makes life on Earth possible. With this broader perspective on solar flares and their cosmic implications, let's now turn to the ethical considerations surrounding our preparedness for these powerful solar events, examining the responsibilities we hold as a global community. Now turning to the ethical considerations surrounding solar flare preparedness, we must confront the complex dilemmas that arise when balancing technological progress with the need to protect vulnerable populations. As we develop strategies to shield our technology and infrastructure from the devastating effects of solar flares, questions of fairness and resource allocation come to the forefront. Who should bear the cost of these protective measures, and how do we ensure that no community is left behind? One of the most pressing ethical challenges is the prioritization of resources. Upgrading power grids, hardening satellites, and implementing early warning systems require significant financial investment. In a world where resources are limited, decisions must be made about which regions or systems receive priority. Should wealthier nations with more advanced infrastructure take the lead, or should efforts focus on protecting areas that are most vulnerable to the cascading effects of a solar storm? This raises concerns about equity and the potential for widening the gap between developed and developing nations. Another ethical dilemma lies in the balance between technological advancement and risk mitigation. While innovation drives progress, it also introduces new vulnerabilities. For example, the increasing reliance on interconnected technologies, such as the Internet of Things, creates a web of dependencies that could be disrupted by a single massive solar flare. How do we weigh the benefits of these advancements against the risks they pose? Should we slow down the pace of technological development to ensure greater resilience, or is it more ethical to push forward and address vulnerabilities as they arise? The prioritization of vulnerable populations is another critical issue. In the event of a major solar flare, those without access to backup systems or emergency resources would be disproportionately affected. This includes not only individuals in low-income communities, but also essential services like hospitals, emergency response teams, and public transportation systems. Ensuring that these groups are protected requires proactive planning and a commitment to social responsibility. Finally, there is the question of global cooperation. Solar flares do not discriminate by borders, and their effects can ripple across continents. Addressing this threat requires international collaboration, but differing priorities and resources among nations can complicate these efforts. How do we foster a sense of shared responsibility while respecting the autonomy of individual countries? As we navigate these ethical challenges, it becomes clear that preparing for solar flares is not just a technical problem, but a moral one. It calls for a thoughtful approach that considers the needs of all people, the responsible use of resources, and the delicate balance between progress and protection. With these considerations in mind, we can work toward a future where humanity is not only prepared for the next solar storm, but also united in our commitment to safeguarding the well-being of all. Looking ahead, the role of artificial intelligence in predicting and mitigating the effects of solar flares offers new possibilities and raises further ethical questions, which we will explore in the next section. As we look toward the future, one of the most powerful tools we have in preparing for solar flares is the curiosity and creativity of the next generation. Inspiring young minds to take an interest in space science and solar physics is not just about filling classrooms, it's about equipping humanity with the knowledge and innovation needed to face the challenges of tomorrow. Solar flares, with their dramatic displays of cosmic power, offer a unique opportunity to spark that interest. Imagine a child gazing up at the night sky, captivated by the idea that the sun, our closest star, holds the key to both life and potential disruption on Earth. That sense of wonder is where it all begins. Education plays a vital role in this journey. By teaching young people about the science behind solar flares, we empower them to understand the delicate balance between our technological advancements and the forces of nature. Schools, museums, and even online platforms can serve as gateways to this fascinating field. Hands-on activities, like building simple models of the sun or tracking solar activity through apps, can make these concepts tangible and exciting. When children see how solar physics connects to their everyday lives, whether through the devices they use or the energy that powers their homes, they begin to grasp the importance of this science. But inspiring the next generation isn't just about facts and figures. It's about fostering a mindset of curiosity and problem solving. Solar flares remind us that the universe is full of mysteries waiting to be unraveled. By encouraging young people to ask questions, explore possibilities, and think critically, we're not just preparing them to understand solar activity, we're preparing them to tackle the unknown challenges of the future. Whether they become scientists, engineers, or simply informed citizens, their understanding of solar physics will play a crucial role in shaping a resilient and innovative society. The impact of solar flares on modern life also offers a compelling narrative for young learners. It's a story that blends science, technology, and real-world consequences. By showing how a single event on the sun can ripple across the globe, we help them see the interconnectedness of our world. This understanding can inspire a sense of responsibility and a desire to contribute to solutions, whether through research, policy, or public awareness. As we encourage the next generation to explore the wonders of space science, we're not just investing in their future, we're investing in ours. The more we nurture their curiosity and passion, the better equipped we'll be to face the challenges posed by solar flares and other cosmic phenomena. So let's take this moment to inspire, educate, and empower. After all, the next great discovery or groundbreaking solution might just come from a young mind gazing at the stars, dreaming of what lies beyond. As we bring our exploration of solar flares to a close, it's clear that these powerful bursts of energy from the sun are more than just spectacular cosmic events. They are a reminder of the delicate balance between our technological world and the forces of nature. From their origins on the sun's surface to their potential to disrupt satellites, power grids, and communication systems, solar flares represent both a scientific marvel and a significant challenge for modern society. We've seen how historical events, like the Carrington Event, offer a glimpse into what could happen if a massive solar flare were to strike Earth today. The vulnerabilities in our technology, from GPS systems to power grids, highlight the need for preparedness and innovation, but it's not all doom and gloom. Advances in monitoring and early warning systems, along with efforts to harden our technology against solar radiation, show that we are making progress in mitigating these risks. The key takeaway is this: while solar flares are a natural phenomenon beyond our control, our ability to understand, predict, and prepare for them is entirely within our hands. By staying informed, investing in research, and fostering global cooperation, we can reduce the impact of these cosmic events and ensure the resilience of our modern way of life. So, as we look to the future, let's ask ourselves, how can we, as individuals and as a society, contribute to this effort? Whether it's supporting space science, advocating for better infrastructure, or simply staying curious about the universe, every action counts. The sun will continue to shine, and solar flares will continue to occur. But with knowledge and preparation, we can face these challenges head-on. Thank you for joining us on this journey through the science and impact of solar flares. If you found this video insightful, don't forget to like, subscribe, and hit the notification bell to stay updated on more fascinating topics about our universe. Together, let's keep exploring, learning, and preparing for the wonders and challenges that lie ahead. you.